Let's keep talking about valence bond theory and its main central topic, which is hybridization. How the central atom hybridizes its orbitals so that it can bond with all the surrounding atoms. In our previous example, previous video, we have seen how beryllium chloride, beryllium being in the middle, it will need two hybrids. It will need two orbitals to bind, and because it needs just two, it will combine its 2s and one of the three 2p's to form two sp's. Okay, so let's make sure. So one hybrid will be something like that, and the other one, sorry for the mess, but it will be something like that. And what beryllium chloride has, and this is something that valence bond theory can predict, is that it has empty non-hybridized orbitals. These are two 2p's that are empty. Beryllium chloride can act like a Lewis base because it has these orbitals that are empty and that are perpendicular to the axis. These are supposed to be chlorines. They are perpendicular to the axis of the molecule. Another example and it's another Lewis base. Sorry, Lewis acid. Did I say Lewis base? I meant Lewis acid. If it accepts electrons, it will be a Lewis acid. So what would the hybridization look like for boron trifluoride? In this case, boron is the central atom, and it needs to form three hybrid orbitals to combine with the three fluorides. And the larger the overlap between these orbitals, the larger the bond will be, the stronger the bond will be. And let's see what it looks like. Well, boron has only 3 electrons, but it needs to form 3 hybrids, so it will combine 3 atomic orbitals. And remember that you can only get as many hybrids as atomic orbitals you use in the mixture. Therefore, it'll form 3 hybrids, each of them being an sp2. Okay, and this sp2 has the shape that you see here, and it forms 3 of them. And you cannot appreciate the tiny tail that these sp2 will have. Actually, I understand why they didn't write it. It looks pretty ugly. But just so you know that these sp2 usually have a tinier tail on the other side that does not participate, of course, in the bond. So what, again, valence bond theory predicts is that there is a 2p perpendicular to the plane of boron trifluoride that is empty and that does not participate in the hybridization, and it can accept electrons, therefore acting like a Lewis acid. And you may have seen boron used in organic chemistry to enhance the electrophilia of some electrophiles, because it actually will accept electrons in this orbital. More examples of hybridization. The now already famous methane. Carbon, the central atom, needs to form 4 bonds with the hydrogens. Therefore, it needs to involve 4 atomic orbitals, and it will involve the 3 2p's and the 1 2s to form 4 sp3s. And again, the sp3s will be in the direction that VSCPR already predicts, that is, being as farther away from each other as possible to minimize repulsion. And again, the hybrids, I will insist, they have a tail in the back that you don't see here, but it's kind of ugly. Anyhow, well, this is, again, I'm sure you're very familiar with the sp3. This is the basis of organic chemistry, so no questions here. It may be new to you when you have a central atom surrounded by more than 4 surrounding atoms. In this case, phosphorus needs to come up with 5 hybrid orbitals, and well, phosphorus has the 3s, has 3p, and it will need to use an extra 3d to form the 5 hybrid orbitals. And that those 5 hybrid orbitals will be labeled sp3d. And again, they will be separated from each other as farther away from each other, forming this bipyramid trigonal that you see in this picture. Like methane, valence bond theory predicts that phosphorus has no lone pair in the middle. Well, Lewis structure already told us that. But so in this case, you can see that valence bond theory, at least at this level, does not predict more than what Lewis structures could already tell us. Okay, so just making sure that we get the idea to build the hybrids orbitals in the central atom. One needs to first identify the molecular formula, draw the Lewis structure so that you know how many electrons goes in each of the atoms, and also remember that the orientation of the orbitals will be given by via CPR, and finally building the hybrid orbitals. Let's see if we can understand a little bit more the hybridization, in this case, of nitrogen in these two molecules, NO2 and NO3, both, so nitrite and nitrate. And we're being asked the hybridization. Well, in both cases, it doesn't matter, this one would have resonance, but it has, for nitrate, it has 3 surrounding elements, 3 surrounding atoms, therefore it needs to form 3 hybrids, therefore this has to be sp2. Okay, so let's see, and now nitrite, if of course this one would have resonance structures, so would this one, but in this case, while this one does not, it has a lone pair, it does not form surrounding atoms, this is angled. This means that also 3 atomic orbitals need to be involved, because this nitrogen needs to point to, this lone pair needs to point to an opposite direction. So this will be around 120, if you remember from the first semester, because this lone pair is actually fairly large. It may be a little closer, but wait a minute, this is a double bond, so in any case it will be around 120. This means that there has to be 3 atomic orbitals involved in the hybridization, therefore nitrogen is also an sp2. So the right answer is sp2 for both. And a question for you to think about: do the same for carbon dioxide and carbonate. I will just draw here. Just think about how many surrounding, think about the central atom, both carbon, if both are sp3, definitely this one is sp3. In here there is no lone pair, therefore it has to be sp. Okay, sorry, sp3. This should be, went too fast, sp2, and this one is sp. Alright, hopefully this makes some sense. Notice that at this level the valence bond theory did not predict much other than what you saw in here, the properties of beryllium and boron to have empty orbitals perpendicular to the model, to the molecule. That was a stronger prediction of valence bond theory. At this level, it looks like valence bond theory does not tell us much more than what via CPR and Lewis structure was telling us for these other molecules.